A new interstellar comet, 3I Atlas, speeds through our solar system. In 2017, astronomers detected something extraordinary. An interstellar object later named Oumuamua had entered our solar system. It was fast, it was strange, and it defied expectations. 2 years later, a second interstellar object, Comet 2I Boris, confirmed that Oumuamua wasn't a fluke. Now, in 2025, it has happened again. A new object has appeared on the radar, and this one is called A11P I3Z. Unlike Oumuamua, which we noticed 5 days after it flew past Earth, this time we're ready. Music, spotted on July 1st, 2025, and listed by the International Astronomical Union's Minor Planet Center, A1PI3Z raised eyebrows in the astronomical community. It first showed up in the Near-Earth Object Confirmation page flagged for follow-up. But this wasn't just another rock on a long elliptical orbit. The moment astronomers began fitting a trajectory, the signs were clear. This object isn't from around here. Its orbital path is sharply hyperbolic, meaning it's not gravitationally bound to the Sun. That's a defining trait of interstellar objects. Preliminary calculations suggest an eccentricity of around 6, the highest ever recorded for any object passing through our solar system. That confirms what many suspected from the start. This object isn't just interstellar. It's on one of the most extreme interstellar paths we've ever seen. Now, objects are considered interstellar if they travel faster than 42 km, the Yao-Suas minimum speed required to escape the Sun's gravitational pull. A11's incoming speed is roughly 66 km/s relative to the Sun, which is way above the escape velocity required to leave the solar system. But to confirm its path, astronomers needed more data. Not long after the initial detection, early August, images were uncovered in archival Atlas survey data stretching back to June 25th. With those new data points, astronomers could run more reliable fits, and the evidence remained compelling that A1PI3Z is in fact an interstellar visitor. It has now been officially catalogued by the Minor Planet Center as 3 Atlas, the third confirmed interstellar object ever detected in the solar system. From the trajectory, we know that 3IE Atlas will reach its closest point to the Sun on October 27, 2025, at a distance of about 1.4 astronomical units. Unfortunately, Earth will be on the other side of the Sun when that happens. However, its closest approach to Earth comes on December 17th at a distance of 2.4 astronomical units. Far enough that it poses no danger, but close enough for telescopes to keep an eye on it. After that, it will continue outward, passing near Jupiter's orbit around March 10, 2026. Early images taken by astronomers show the object at a visual magnitude of around 18.8. Based on its brightness, if it has a typical reflectivity, the object could be about 20 kilometers wide. That's significantly larger than Oumuamua and even bigger than 2I Boris. However, it's possible that it's more reflective or even emitting gas, which could skew size estimates. But here's where things get interesting. If the object begins to show any non-gravitational acceleration similar to what was observed with Oumuamua, that could open a whole new line of investigation. Such accelerations can be caused by outgassing, or in some exotic theories by artificial propulsion, which is why all eyes are now turning to the James Webb Space Telescope. With its powerful infrared capabilities, Webb could detect thermal emission from the object, revealing its temperature, size, and maybe even its shape. Another intriguing feature is the object's inclination, which is nearly 175 degrees, a steep angle that practically guarantees that it isn't a native of the solar system. In fact, the orientation of its orbit suggests it may have originated from the Milky Way stellar disk, the flat plane where most stars in our galaxy reside. And that opens up a tantalizing idea. If we can determine its incoming velocity and direction precisely enough, we might be able to trace it back to its origin system. 3 Atlas will only be within range for a short time. It may brighten as it nears the Sun, but with Earth out of position, our chances to study it are limited. Combining ground-based telescopes, space observatories like JWST, and perhaps even spectroscopic studies could tell us if it's a comet, an asteroid, or something entirely unexpected. New reports suggest there may be signs of cometary activity, but for now it remains unconfirmed with much more data still to come. With the Vera C. Rubin Observatory now online, its decade-long legacy survey of space and time is expected to dramatically increase the number of interstellar objects we detect, turning rare encounters into routine science. In fact, the telescope has already released its first image and has detected several new asteroids, including some near-Earth ones. Over 400 years ago, Galileo pointed a small telescope at the night sky and changed astronomy forever. Today, we stand at the edge of another revolutionary shift. Enter the Vera C. Rubin Observatory, which is built to sweep the sky like a scanner night after night and catch the universe in motion. It will catch everything. Asteroids streaking across the sky, stars suddenly flaring or fading, and even clues to physics' greatest mysteries, dark matter and dark energy. The telescope is named after Vera Cooper Rubin, who changed astronomy with one question: why aren't galaxies spinning the way they should? Based on Newtonian physics, stars at the edges of a galaxy should orbit more slowly than stars near the center. But Rubin found that they were moving just as fast. That shouldn't be possible unless something invisible was holding the galaxy together. Her work provided the first convincing observational evidence for dark matter, and now the observatory named after her is poised to pick up right where she left off. The Vera C. Rubin Observatory has now begun its 10-year mission, the Legacy Survey of Space and Time, or LSSD. The plan is to photograph the entire southern sky again and again and again, every few nights for a decade. By stacking, comparing, and analyzing these repeat observations, astronomers hope to uncover what changes, what moves, and what hides in the dark. So how do you pull that off? At the heart of Rubin's mission is the largest digital camera ever built for astronomy. About the size of a small car, it holds a 3.22 GPa imaging surface, made up of 189 ultra-sensitive sensors, each one larger than a typical medium-format camera sensor. These are arranged into 21 modules, called rafts, all sealed in a vacuum and chilled to 48 degrees F to reduce electronic noise. At this temperature, they can quietly capture even the faintest glimmers of light from deep space. The focal plane itself spans over 2 feet across. Each exposure covers 3.5 degrees of sky, wide enough to fit 7 full moons side by side. It takes just 15 seconds to capture a shot, and only 2 seconds to download it. So, what is it looking for? The LSST has 4 main science goals. Number 1, dark matter and dark energy. Rubin will map billions of galaxies and trace how they move and cluster over time. That will help scientists measure how fast the universe is expanding and whether that expansion is changing. This could provide vital clues about the nature of dark energy, the mysterious force accelerating cosmic expansion. Number 2, watching the sky change. With its rapid sky scans, Rubin can detect supernovae, gamma-ray bursts, flickering quasars, and even the first visible signs of a newly forming black hole. Within about a minute of capturing an image, Rubin's system compares it to previous ones and flags anything new or strange. It's one of the fastest alert systems ever built for astronomy. Number 3, planetary defense. Rubin will track near-Earth objects. Its wide field of view and rapid cadence mean it can detect thousands of asteroids per night. And number 4, cataloging the solar system. Rubin will peer beyond Neptune into the Kuiper belt and possibly beyond. By discovering and studying distant icy bodies, it could help us understand how the solar system formed and whether there are still undiscovered objects hiding at its edge, and its first light images already are delivering on that promise. This composite of the Trifid and Lagoon Nebula is one of the first images released by the Rubin Observatory. Made from more than 678 exposures in just over 7 hours of observing time, this one explores details in the 2 massive star-forming regions several thousand light-years away from Earth. In another, the Virgo cluster reveals more than 2,000 galaxies in a single frame, made from over 1,100 images captured by Rubin. It begins with a close-up of a spiral galaxy and then zooms out to reveal about 10 million galaxies. And here it showcases 46 subtly pulsating variable stars, in an early glimpse of the dynamic sky the observatory will reveal. In the next decade, it's expected to detect up to 100,000 of these stars, reaching distances of over 1 million light-years. Also, during its 10 hours of observation, the observatory discovered 214 never-before-seen asteroids in our solar system, including 7 near-Earth asteroids. None are dangerous, but that's not the point. The point is how fast and efficiently Rubin can detect them. All other ground and space-based observatories combined discover around 20,000 asteroids in a year. In comparison, the observatory is expected to uncover millions of new asteroids within just the first 2 years of the Legacy Survey of Space and Time. How mind-blowing is that? Every night, Rubin will scan the sky looking for anything, that moves, flares, or fades. That also includes objects that don't behave the way we expect, like Oumuamua, the first known interstellar object to pass through our solar system. If anything like it enters Rubin's field of view, the observatory will detect it and alert.